Okay, great. Thanks for the kind introduction, and I'm really, really happy to be here. I want to thank the organizers for a very, very excellent workshop. It's really a privilege to be here, but I also want to thank all of you for still being here on the last day of the workshop. I know that Paris is a tempting city. So today I want to tell you something about a project on which we worked a long, long time. And you can see there's an impressive list of authors for a pure theory paper. And I want to take my time, because of that, to actually motivate why we care about this particular problem. Because we put a considerable amount of effort in that. And this may seem obvious to some of you or many of you, but I still want to make a case that we believe that this is really was worth our while. And afterwards, I want to mention the key ideas that led us to establish such a result, and also the main result. I will discuss it a bit. And later on, I thought a long time about that, but I'm actually going to give you a proof history and not a proof idea, because we combine methods from several fields of mathematics, and I think it would be too intense to go into details into any of those, so I rather sketch the main ideas, and then of course I give a conclusion and an outlook. And the full title of this talk should actually read Recovering Unitary Channels. So this means process tomography from few average gate fidelities with respect to random Clifford gates. And these random Clifford gates are important, and these are the main reason why this project was rather challenging. So let me start with motivating it. Why are average fidelities interesting? The average fidelity of a channel is defined that way. So this is not the most general definition. In this definition, I actually assumed that one of the two channels where we want to measure the average fidelity is unitary, because then we can just then the adjoint channel is the unitary, it's just the adjoint of the unitary. But the average fidelity is just, you start with a pure state, then you apply the channel, then you apply the adjoint channel to which you want to compare it to, and then you measure the overlap with the state you started with. And then you average it over all possible pure states. And this gives you a single number, a figure of merit, that kind of quantifies how close an arbitrary channel T is to the second channel C. For instance, if they would be the same, it would be just 1. And otherwise, it goes down. The advantages of such a single measure of closeness is, most importantly, it can be estimated very efficiently if one of the two structures, one of the two channels, in my case the channel C, is highly structured. For instance, if this is the identity gate, then it's easy. Or if this is more general, a Clifford gate, then this is also easy. And I want to point out two cool techniques to do so. And the first one is direct fidelity estimation. This was developed by Steve Lamia and Yi-Kai Liu in 2011. And it basically uses importance sampling. And the idea is rather cute. And I just want to briefly explain it for states. Like you all know that states also have fidelities. There are state fidelities. And the concept is very similar for channels, but for states it's easier. Suppose one of the two states we want to measure is pure. Then the fidelity is just a trace of the product of the density operators. And now you know that in every finite Hilbert space, you can construct a unitary operator basis, like the Pauli basis. And then you can, in principle, represent both of these states by coefficients with respect to their Pauli basis. Now, if you want to do fidelity estimation, you assume that you know one of these, say C, and so you know the expansion coefficients. And then something interesting can happen if the state you want to compare the unknown state to is very structured, then this expansion coefficients can have a lot of zeros. And this kind of tells you already that if you want to compute the average fidelity, the trace in a product, that would be the same as the product of the coefficient vectors. But because one of them has a very, very small support, it suffices to choose fewer samples. You just measure the Pauli matrices with respect to those expansion coefficients that don't vanish. And this allows you to really reduce resources. And perhaps even more interestingly and importantly, this is a huge open field, is the field of randomized benchmarking for quantum gates. Randomized benchmarking was developed, I think, in 2006 by Joe Emerson and co-workers. And it's another idea of directly estimating average fidelities for quantum gates or arbitrary channels. And this is really, really remarkable because unlike standard state, process tomography methods, or direct fidelity estimation, this procedure is provably robust with respect to state preparation and measurement errors. So this is a huge advantage over traditional estimation techniques. And more or less the idea is that you use a certain group. Most often it is the Clifford group. And then if you want to measure the average fidelity, let's say, of an implementation of a gate with respect to the identity, or like with respect to the ideal gate, then you just apply random Clifford rotations. You make a sequence of random Clifford rotations, and because the Cliffords form a group, in the last step you can apply an inverse gate that inverts all the Clifford rotations you did before, and so in theory you would have done nothing. And then you send in a state, and you measure the survival probability with respect to the same state, and this is likely to decay because if you have errors, then you won't exactly recover the original state, but only approximately. And you can do that for several sequence lengths and estimate the survival probabilities. And in the end, you can do a fit, and the slope of the fit actually tells you the average fidelity of your implementation of this gate set. And this is robust with respect to state preparation and measurement errors. And this is an interesting feature. But of course, there's also disadvantages with average fidelities. It's just a single number that tells you something about how well you have done in preparing a certain gate. Suppose you want to prepare a channel C, and like what you actually managed to do in the lab is T, then of course you want this thing to be large, but it's still not clear what it actually means. Of course, close to 1 is good, close to 0 is very bad, but beyond that, it's actually not so clear what it means. And Robin Blum-Cahoot recently published a paper where he pointed that out. And perhaps even more importantly, it's just a single number. So it doesn't give you actionable advice if you see that the number is not so good. So suppose you work really hard to prepare your favorite gate in the lab, you measure it, you do randomized benchmarking, and then you find out that the average fidelity is 0.7. Like, what should you do? It just tells you that you did a poor job. This is in contrast to quantum process tomography. So quantum process tomography is the art of fully reconstructing an unknown quantum channel using quantum measurements and feeding in input states. And this is kind of the other extreme of a single parameter. And usually, a channel is a rather complicated object. It has many degrees of freedom, so you have to feed in a quantum state to the channel. Then afterwards, you apply a measurement, then you repeat that many times to get an idea of the probabilities. And then you have to change input states and output states in order to reconstruct the channel T. And if you do that, there's huge advantages. Namely, you get a full description of the channel. I mean, of course, noise will will corrupt that a bit. But in principle, you know exactly what your quantum mechanical system is doing, and this gives you actionable advice. For example, if you are not doing so good, like this could tell you like where you have to tweak a bit more. And these techniques, traditionally they use linear inversion, but there's more modern techniques, are also robust towards additive noise. So in quantum mechanics, we always have to repeat experiments many, many times to get frequencies that are close to the actual probabilities that the theory tells us. But we can never fully get there, so there's always like some offset. But process tomography is at least robust with respect to these imprecisions, but there's of course disadvantages. The most important one and obvious one was often mentioned in this talk already. It's extremely costly. Suppose you have a quantum channel acting on a D-level system, then the density operators have dimension D squared. Channels map density operators to density operators. This is dimension to the power of 4 many degrees of freedom. This is a large number usually. And another problem is process tomography, unlike randomized benchmarking, is very susceptible to state preparation and measurement errors, because if you feed in the wrong state, kind of your observation don't match the model that you use to do linear inversion later on. And this is really, really an important problem and drawback of process tomography. So the title also said something about unitary channels. Why do I care about unitary channels? Why do I want to reconstruct unitary channels? Well, my collaborator Jens Eisert always likes to say, it's a bit too much for me, but he always says that like in physics, when we learn quantum mechanics, we are always presented with a Hamiltonian by the teacher, and then we compute all sorts of things. But nature is not really that way. Like, I don't know, nature just doesn't give us a Hamiltonian. Hamiltonian is us modeling nature. But if I were to present you a black box with a quantum evolution inside, then you wouldn't know what the Hamiltonian is. And one way to find out Hamiltonian dynamics is unitary. So it introduces, in the ideal case, a unitary evolution. And if we were able to reconstruct any unitary channel, we could also infer Hamiltonians from there. For me, this is Jens Eisert's interpretation. I care more about building quantum computers in the not-so-far future, and quantum gates. The entire circuit model of quantum computers heavily uses unitary gates. A quantum algorithm just has unitary gates applied to it. So unitary gates feature really, really prominently when we think about actually using quantum mechanics to do something new. And related to this, coherent errors that can happen in circuit models are often also close to unitary. And I care also quite a bit about fault-tolerant quantum computing. I think this is one of the big challenges that we have. And recently it was observed that coherent errors in a quantum algorithm are the worst kind of errors if you want to achieve thresholds for a threshold theorem. So if you build a quantum circuit and you somehow do unitary over or under rotations, which sum up to coherent errors, then this is very, very bad if your ultimate goal is to achieve fault tolerance. I'm happy to talk more about that offline, or if you feel free to ask me a question at the end, what I mean by that. But all these kinds of important problems are approximately unitary channels. So somehow it's probably worthwhile to think about how we can reconstruct them efficiently. More pragmatically, unitary channels are somehow the most extreme quantum channels there are, because a general quantum channel on a d-level system has d to the 4 degrees of freedom. A unitary channel only has d squared many. So somehow the number of degrees of freedom a unitary channel has is much, much lower than a general channel. And more precisely, if you look at the Choik-Hamilkovsky and the Choi matrix of a channel, so remember there's like the Choik-Hamilkovsky isomorphism maps every quantum map to a bipartite density operator. And this bipartite density operator is positive semi-definite if and only if the original channel is completely positive. This is the case in quantum. And it's trace preserving if and only if one of the partial traces is proportional to the identity. So with every channel, you can associate a density matrix. And the density matrices associated with unitary channels are very, very special because they're pure. They're pure states. And they're not only pure states, but they're also maximally entangled. So there's a lot of additional structure when you think about unitary channels only that is somehow diffused and washed out if you think about more general channels. But most importantly, like there's just d squared degrees of freedom, so maybe we can get by with fewer measurements. Remember, full process tomography requires d to the 4. Determining d to the 4 parameters, here we only have to determine an order of d squared. Well, let's exploit that, right? Maybe we can reduce the number of measurements required. So this concludes the motivation why I actually am interested in doing process tomography on unitary channels with average gate fidelities. This would combine a lot of the perks that is here. And in order to do so, there's really 3 key ideas that I want to point out. And the first one is actually known for a long time now, because in 1999, the Horodetskis wrote a great paper that relates the average fidelity, gate fidelity between 2 channels to the entanglement fidelity associated with the channels. But you can in turn rewrite the entanglement fidelity of the channels in terms of the channel's Choi matrix, and what you get is just this very simple formula. On the left-hand side, you have the average fidelity, and on the right-hand side, you have a scaling factor. You have an offset, but this is just a trace inner product of the Choi matrices. And This allows you to view the average gate fidelity between two channels actually as a single bell type measurement of the unknown Joy matrix associated with the channel you want to reconstruct. So just this, if C is a unitary gate, then this is again like a maximally entangled bipartite state. It's pure, and so this trace inner product is just the same as the outcome probability of a certain bell type measurement. And importantly, typically or often in process tomography, what people do is they feed in one half of a maximally entangled state. This is like the ancilla-assisted quantum process tomography protocol to convert the task of reconstructing a channel to the task of reconstructing a Joy matrix. And the Joy matrix is just a density operator, and so you can directly import all the techniques we know and love for doing state tomography to process tomography. Well, this is a neat shortcut, because the average gate fidelity, determining it, doesn't require ancilla systems. But this formula tells you that nonetheless you can interpret it as if you were performing a quantum state tomography measurement on the ancilla-assisted Joy matrix of the channel. And of course, if you vary the unitaries with respect to which you measure your average gate fidelity, you efficiently implement different bell measurements. And you can do a lot of them. And every new bell measurement gives you a new observation, a new bell type measurement. And if you do that long enough, you can actually do process tomography. You can do state tomography on the Joy state level. And this result goes back to Shelby Kimmel and those guys in 2014, and is one of the key ideas that we want to exploit. There's an obvious drawback of this. This is still very costly. Like we haven't done any dimension reduction. We still need to play this game in order of d to the 4 many times in order to do full process tomography for arbitrary channels. But this is the first main ingredient. The second main ingredient is what I call here the compressed sensing paradigm. Remember that if U is a unitary channel, then the Joy matrix is pure and maximally entangled. In math terms, this means that the matrix is constrained to have unit rank. And this is an interesting constraint because it's not so easy to grasp. You can't penalize rank because it's a non-convex function, but it still tells it that like the model is very limited. There's not so many matrices that can have rank 1. And the compressed sensing paradigm allows for exploiting this feature in an unsupervised way. So you can penalize or you can promote this purity assumption without actually having to know the eigenbasis of the matrix or like where the matrix actually is. And the idea is always the same in compressed sensing. It's choose your measurements randomly. This is very, very important for the proof techniques, and it allows you to avoid hard contrived instances. But kind of compressed sensing tells you just pick linear measurements at random, pick sufficiently many. What does sufficiently many mean? It just means like, well, it should be proportional to the number of degrees of freedom your system has. A unitary channel has d squared degrees of freedom. So let's choose d squared random unitaries and measure those average fidelities. This gives us some data points. But of course, the entire space of channels has dimension d to the 4. So these measurements, these number of data points, doesn't suffice to nail down the channel at all. It gives constraints on the amount on the channels that are allowed, but there's infinitely many solutions to this problem. Just because we're not informationally complete, we're way too lazy. We just sample d squared many measurements, not d to the 4. And then, in order to single out the actual state, compressed sensing proposes a classical post-processing scheme. So you use the observations you made, you use them as a constraint in a tractable convex optimization problem, and then you minimize a penalizing function in order to promote the low-rank structure. And the simplest way to do that, at least for positive semi-definite matrices, which is the case for Joy matrices, they are positive semi-definite because unitary channels are completely positive, is to just minimize the least squares fit error to the observation you made. It's a very natural thing to do. Like you have a couple of observations, and then you go over your entire parameter space and try to reproduce them as good as you can with respect to constraints, namely that X is positive semi-definite and that it is maximally entangled. Because we know that the Joy matrix of a unitary gate has to have these properties. And voila, this actually works. And Shelby Kimmel and Yikai Liu, one of the collaborators on this project, actually could show that this procedure works with high probability if the unitaries, C1 to Cm, are chosen uniformly from the Haar measure, as random as possible. This is always good for complex tensing, makes your life easier. But there's, of course, still a drawback. I mentioned at the beginning that like average fidelities can be estimated efficiently for structured unitaries. If you want to measure average gate fidelities with respect to Haar random unitaries, you at some point have to implement a Haar random unitary. That's not easy. It takes exponentially many resources. So measuring average gate fidelities with respect to Haar random unitaries is not easy. So this is a nice theoretical result, but it's not the end of the story, arguably, because the measurements are not practical. So we need a third key idea to somehow get away from Haar random unitaries to something that is more structured and actually can be implemented. And this is the key idea of number 3. And this means approximate Haar random unitaries by unitaries chosen at random from the Clifford group. And just to bring us all on the same page, the Clifford group is a subgroup of the full unitary group, and it's the symmetry group of the generalized Pauli matrices. So in d dimensions, you can always define generalized Pauli measurements, and the Clifford group are those unitaries that if you sandwich a Pauli matrix from the left and the right, if you adjoint it with such a unitary, then it maps the Pauli to another Pauli matrix up to a global face. So for a single qubit, for instance, the Clifford group is just the Pauli group itself, because Paulis commute or anti-commute in dimension 2, and a T-gate. And if you want to go to more multi-qubit systems, then a full set of generators is always the Pauli group together with T-gates for individual qubits and C-naughts. So this is a rather structured group. And it's importantly, the average gate fidelity with respect to Clifford is always particularly easy to estimate. Like if you use direct fidelity estimation, then you can exploit the fact that like Clifford unitaries, if you represent them in a Pauli basis, are always have very, very small support. Andrea mentioned that on Tuesday as a defining feature of stabilizer states, and Clifford circuits are just a generalization thereof. And it's even better for randomized benchmarking, because randomized benchmarking was invented for the Clifford group. So if you want to squeeze in another Clifford element in your randomized benchmarking procedure, then this should work well, because it's exactly the structure they already use. And perhaps most interestingly, at least for multi-qubit systems, so if the dimension is a power of 2, the Clifford group is a unitary 3 design. Well, what does this mean? It means that the Clifford group is a very good curvature or quadrature, a finite quadrature for the full unitary group. So the full unitary group is a Lie group, so it's something round. So I've made a cartoon of a ball here. So think of this as being the full unitary group endowed with a Haar measure. Then what the Clifford group does, it's a discrete subset of this full unitary group that is very, very structured and has the particular property that if you were to integrate polynomials of degree, it's a 3 design, this means if you were to integrate polynomials of degree 3 in the matrix elements of your unitary and degree 3 in the complex conjugate of this matrix elements, if you were to integrate it over that, you can as well integrate it over the Clifford group itself. So it's a discrete approximation for numerical integration and approximation. And this kind of tells you that it evenly approximates the unitary group. And remember that I complained about this result by saying that, like, yeah, we have to like draw Haar random unitaries in order to make the proof work. Well, this also tells you that probably Cliffords are a good way to get away from the unitary group assumption. And exactly, the fact is that random Clifford unitaries actually accurately mimic Haar random unitaries up to a certain degree. In this case, degree 3. And this gives us room to work with. And there's a small drawback associated with that. This feature is only true in multi-qubit dimensions. In other dimensions, these curvature properties are not necessarily true. Okay, so far, those are the key ideas. And so we all joined forces to combine them. And as you can see, this is a rather long and impressive list of authors for a single paper. But we all played our part. Like Shelby Kimmel was responsible for like the part of like using average gate fidelities as measurements. David Gross and Jens Eisert were some of the inventors of compressed sensing back in 2011, and Martin Clich and me also did a lot of the heavy lifting. Here's the main results. Long story short, it works. In multi-qubit dimensions, this is essential for us. It actually suffices to choose a number that is proportional to d squared, not d4. We have to invest an additional log factor, average fidelities with respect to random Clifford gates, to reconstruct any unitary channel. And the reconstruction algorithm is again a least squares fit over the observations that you made. This is a tractable convex optimization problem. Here's the advantages of our results and why I think probably it's worthwhile telling. This is an almost quadratic improvement over full tomography for unitary gates. And I think this is relevant for the noisy intermediate scale of quantum devices where we are in today. Average gate fidelities with respect to Clifford gates can be efficiently estimated in experiments. So it's not bogus what we propose. And if we use randomized benchmarking to get these numbers, we can do that in a spam robust way. So we have a scheme for process tomography that is actually robust towards state preparation and measurement errors. And the reconstruction is also stable to additive noise corruption. So if we don't get the average gate fidelities exactly, it's not so important. And also, but this is probably a bit more tricky, is the reconstruction is also stable against the model assumption of unitary channels. So if my channel is not unitary, but it has like the largest, like the unitary is the dominating part, and it has like a small tail with higher Krauss rank, then we still get the unitary part of that channel. So there's instability also with respect to the unitarity. There's of course disadvantages as well that I want to list and defend a bit in the monologue. The result is only valid for qubit dimensions, but I would argue that's the most relevant case anyway. So far we only cover unitary channels. That is true. The details in the proof are rather tricky. It's actually not obvious or like very hard to generalize it, but I think it's still plausible that, like, I don't know, when I have regained my strength, it's probably possible to show that this actually works for channels with arbitrary Krauss rank if we put in the Krauss rank in the number of measurements. The constant C here is embarrassingly large. There's a reason why I called it C. But numerical experiments that I'm going to show you in a minute suggest that this is a much, much better constant, that the constant is actually 4.8 or something. This is probably the biggest drawback. The reconstruction is a convex optimization problem. It's a least squares fit over the set of all channels, but this still corresponds to an STP on d squared times d squared matrices. This is a large number. These are large matrices. So this solving them requires a lot of memory. So as you probably heard, like Andrea was mentioning that STPs tend to be slow for large problems. And it's not the problem that they like take a lot of runtime, it's the storage that is the problem. And this is also a problem for us. But I think that recently developed sketching algorithms or non-convex algorithms actually allow to reduce the required storage to an order of d squared again, which is to be expected because the solution is a unitary channel, so the solution, only to store the solution, it requires d squared many parameters, but I think it's possible to press down the storage there as well to go to even larger systems. Here's a numerical experiment that shows how that it actually works. So down here you see the Hilbert space dimension. So this is reconstructing a single qubit unitary. Yes.
Sorry, so what is the reconstruction method?
With the least squares fit. Thanks for interrupting this. Yes. Kind of you measure average fidelities, and then like you kind of, I gave you a formula how you can write the average fidelity as an inner product on the level of joy matrices. This is your channel. This is the degree of freedom, the search space, all possible channels. And the constraints are just that like this is a unital channel. So that the joy matrix of this channel is positive semi-definite, is a positive semi-definite constraint, and that the partial traces are proportional to the identity. That's an affine constraint.
So So in tomography, usually if you do these squares, it's not a good estimate.
Here it is.
Why is there
Yes, it's a hidden compressed tensing algorithm that I do here. In compressed tensing, probably if you remember the talks of the old days when David Gross and Jens Eiser toured the world, they always minimize the trace norm. Yeah. But in quantum state process tomography, the trace norm is fixed anyway because you know that your matrix is, the density matrix is positive semi-definite and has trace 1. So surprise, surprise, the trace norm is 1. So why should I minimize that? So actually, the compressed tensing protocols from the old days correspond to a feasibility problem with respect to the constraints. And everything I did here is I used Tikhonov regularizations to push the constraint into the optimization. Like one way of solving a feasibility problem is to minimize the constraint. This is what I do here. And it has an additional advantage that we don't have to have like any assumptions on the noise that is there. I mean, there's just the only parameters that enter here are estimates for the average fidelities. Okay, great. Here's numerical work. So down here, you have actually the Hilbert space dimension. So the first bar is for 2 qubits already. And what we did here is we sampled a random unitary channel, and then we played the game. Like measure average fidelities, sufficiently many. And the number of average fidelities we measured, the square root of those is listed here. So you can see like here, 2 qubits. Here, this would be 25 measurements. Random measurements with respect to, on the left bar, these are random unitary gates. Theoretically, you can do that. You can just sample your control, your comparison gates from the unitary group, and on the right-hand side from the Clifford group. And you see a phenomenon, this is actually typical for these quantum compressed tensing type phenomena. You see a very sharp phase transition. So blue is bad. It means that you are very far away. Your estimate is very far away from true value. And 0 is very, very good. It's basically exact reconstruction. And you see that in the beginning you do very, very poorly. And then suddenly you hit a sweet spot. There's a phase transition. And then you like do everything correct. And you can at least like this is in the idealized case of no noise. So after you hit a certain threshold, you actually reconstruct perfectly. And you can also see like here's the same done for 8. So this would be 3 qubits and 4 qubits. And you see there's a roughly linear behavior. And the numerical constant actually suggests that you need a number of like 5 times d squared many measurements to make this work. And this also should demonstrate that actually, like, although we use SDPs, we actually can go to certain system sizes. So like these are 4 qubits, so the channel dimension is pretty high for that already. But we can still do it there. And I think you can push it to higher qubits if you pull off a few tricks. So here's another numerical experiment for those of you who like log-log plots. I'm not one of them. But here we actually use reconstruction where the experiments are also prone to noise. So we did again some numerical simulations, but then we corrupted the average gate fidelities, each average gate fidelity with a noise corruption. And for different noise strengths, this is again like here we vary the number of measurements we do. This is now just for 3 qubits, just we fix the dimension. And here we vary the number of measurements that we're doing. And this tells you the logarithm of the reconstruction error that you get with respect to noise. Well, unsurprisingly, if you crank up the noise, the reconstruction error becomes bigger. But it's still rather, rather small. So you can actually, even in the presence of noise corruption, you get something that is actually close to what you're looking for.
In the previous plot, there was some noise as well, right?
No. Here, we didn't assume any noise.
So you just have the values of the
Yes.
values.
Yes. So kind of we just played a game, like choose a random Haar random unitary channel, then choose random measurements, compute the average fidelities on a computer, forget the original channel, do the reconstruction, check if it's the same.
So how does it work? So with some probability you will get exactly the channel?
Yes, but these are also averaged. Like we averaged for each dimension, for each number of measurements we used. We did 100 runs of the experiment, and like this is the frequency of success.
Yeah, so the error here comes from the bad choices.
Yes, exactly. So there's a sharp phase transition for a certain sweet spot of number of measurements, and that sometimes works and it sometimes doesn't, and this tells you why there's a very small blue region here. Thanks, I should have said that earlier. But here there's actual noise. But you can still see that it goes down. And if you were to like convert this into normal numbers, then you would see that there's a roughly linear dependence between the noise strength and the reconstruction error. Okay. Maybe I shouldn't talk too much about the proof history anymore, but I can briefly rush through it. I want to tell you it's been a long road. We've been working on this project for almost 5 years, and here's why. First, we had to understand the geometry of these average gate fidelity measurements, and this is actually quite interesting because these Choi matrices of unitary channels give you maximally entangled states, but maximally entangled states, if you look at the affine hull of those states, they don't give you all of state space. So like you only can sample from an affine subspace, and this makes things a bit trickier. We first had to understand that. This is probably like, I don't know, an exercise in convex geometry, and it was the easiest one. The second one, this was the hardest one, as we had to develop completely new comprehending techniques to tackle this problem. Probably you remember older talks by David Groß and Jens Eisert maybe, where they said that compressing works for Pauli measurements. Well, Pauli measurements are special because they are unitaries and they are full rank. The measurements here are the opposite. They are rank 1. So their proof technique fails spectacularly and can't be applied to this scheme. So we actually had to develop completely new compressing proof techniques, and the way we did that, and of course it's not only us, but like also the compressing community helped, is we went back to old techniques in random matrix theory developed by Gordon in the 70s. Gordon's escapes through a mesh is a famous example. Then we somehow had to generalize this because these old techniques only apply to Gaussian random matrices. Well, surprise, this is not a Gaussian random matrix either. So we had to generalize this. And then we also had to like get away from these unitary gates in order to make it valuable for Clifford gates. So we also had to de-randomize it. So this was, well, a not so easy problem in large dimensional probability theory to solve, I would say. And finally, we had to show that the Clifford group is a sufficiently good approximation of the unitary group that we can use the compressing techniques that we developed. And this was also a not so easy exercise in representation theory. And to make matters worse, even if we understand the representation theory of the Clifford group, like something like a Schur-Weil duality, say, then these things are still complicated because it's like you apply a unitary on like one part of a system, but you have a second part of the system as well, and then you have to compute averages of tensor products. Well, we also had to develop a new kind of Weingarten calculus to do that, actually. So that's a short proof history. I think I'll skip the sample complexity part and want to conclude. So in summary, we proposed a process tomography procedure that uses average gate fidelities with respect to random Clifford gates. We proved that an order of d squared times log d, many such average fidelities, suffice to reconstruct any unitary quantum channel with high probability. And the reconstruction is actually achieved via solving a convex optimization problem. There's obvious questions for future work. One of them is, of course, generalize this result to cover channels that have higher Krauss rank, let's say 2, 5, or like a constant Krauss rank. I think this is doable. And to find better algorithms to solve the convex reconstruction problem. And finally, if you are interested, here is the archive version of our paper, but I actually want to point you to Chris Ferry's GitHub page, because I think many of you know Chris Ferry, but I don't know if you know that he has a GitHub page where he does open reviews. So if he likes a paper, he actually reviews it for free, not for a journal, and puts it on his GitHub. And he did this for this paper.
Also if he doesn't like it?
Also if he doesn't like it. Thank you.
Okay, let's thank Richard for the